So let's do a quick review of the stuff we talked about last time we met. So a couple big concepts. Fundamental theorem of algebra. Remember what that tells us is that the degree of the polynomial tells us exactly how many complex zeros the polynomial is going to have, right? Including multiplicity. So if I have a factor with a multiplicity of 3, then that's going to give me 3 zeros instead of just 1, right? If it's a linear factor with a multiplicity of 0. Like if I had x cubed as one of my factors, then x equals 0 is going to be, that's going to count as 3. Along with the fundamental theorem of algebra, we got two other corollaries. We got the complex conjugate root theorem, which very simple. All it says is that imaginary zeros always come in complex conjugate pairs. And then another one that we're not really going to use a ton for a little while. It's not so, for today it won't be that big a deal. The irrational root theorem says that if we have rational coefficients in the polynomial, then anytime I get square roots, I get a root or a 0 with square roots in it, they're going to come in conjugate pairs also. So for example, I could have something like 2 plus the square root of 3 and 2 minus the square root of 3 would have to go together. And that's, again, that's only if we have rational coefficients in the original polynomial. Okay, but that one, we'll get to that one later. And then we ended up with our patterns, right? We've got 4 patterns now, binomial expansion patterns. So if I've got a 2-term polynomial, a binomial, a lot of times I can use one of these 4 patterns to expand it out, or not expand it, to factor it into smaller factors. Quick reminder, so a squared plus b squared, the sum of squares it's not even a pattern. With that one, the pattern for that one is no pattern. You can't do anything with it. A squared plus b squared, we just leave as a squared plus b squared. It'll never factor. Difference of squares will always factor a squared minus b squared into our conjugate factors, a plus b and a minus b. And then we had the sum and difference of cubes patterns. Let's just quickly review those. So if we have a cubed minus b cubed or a cubed plus b cubed, they always factor into a binomial times a trinomial, right? The way I always organize this in my mind is I remember that the 2 terms in the binomial are just a and b, and the 3 terms in the trinomial are built by the different combinations, the different ways I can multiply 2 things together. A times a is going to give me a squared, a times b is my middle term, and b times b gives me b squared, my last term. Okay? And then all I've got to do, once I know what the 5 terms are in the binomial and the trinomial, the total of all 5 terms, I just need to know where to put pluses and minuses then, right? And the pattern's simple. If it's a cubed minus b cubed, whatever symbol shows up first here between the cubes, that's going to be duplicated in the binomial. So if it's a minus, it's a minus. If it's a plus, it's a plus. And then the next one is going to be the flip of that, the opposite. Okay, so the second symbol that I have to introduce would be the one between the a squared and the ab. If the first is a minus, that's a plus, and vice versa. And then remember the last one, between the ab and the b squared is always plus every time. And it works the same way in both of these 2 patterns. Just depends on which one you start with. Okay? Make sense? All right, so those are the patterns we're going to use quickly. If you want to write them on a whiteboard, that's fine. You can grab a whiteboard. You can write them on paper. Just try those real quick. Just see if you can crank those out from memory. Get a little practice in. If you want flashcards to help memorize those, I've got tons of them. Come get them. Take a second and just try to write those down. Okay, first one, what's the pattern? No pattern. Okay, try the next one, a squared minus b squared. Okay, what do you get for that one? Difference of squares. What's that one? Some brave soul. That's it. A plus b times a minus b. In no order. Either way works. The order is unimportant. Okay, difference of cubes. Take a second and write that one down. A cubed minus b cubed. Okay, let's see. What's the binomial for that one? What's the first factor? A minus b. Okay, what about the trinomial? What's that one going to be? A squared plus ab, and then we always end up with plus b squared. Okay, try the sum of cubes real quick. A cubed plus b cubed. Aubrey, what'd you get? What's the binomial? Good. Very good. Okay, good. Okay, there they are. We're going to use those a ton. Now remember that when you use the sum and difference of cubes patterns, remember that the trinomials are always irreducible. Meaning they're never going to factor, so don't try. They're never going to factor. That's an I. And they're always going to yield complex conjugate zeros. Okay, we'll look at an example in a little bit where we have to actually solve for the zeros of a function, and we'll find out what those complex conjugates look like in an example. Okay, let's try one of these. How about this guy? If we want to solve that equation, what are we going to do? Set it to 0. Okay, first of all, set it to 0. Good. Okay, so we get 54x cubed plus 2,000 equals 0. Okay, so now we could just divide both sides by a constant here, but let's go ahead just to get practice factoring. Good luck, guys. Just to get practice factoring, let's completely factor the left side. Okay, because a lot of, like I think on this first assignment, the 5.4 practice 1, you guys don't really solve any equations. You're just factoring stuff. You're factoring it completely. So let's do that. So if I'm going to factor the left side, what do I always want to try to do first? Every time I factor anything, first step is I always want to try to do what? Say it again, Trey. Yeah, try to undistribute a GCF. What could I undistribute here? What do you think? You're wondering if it's a 2 or a 4, if there's something bigger, probably, right? Okay, I'll give you another little hint on this. After we undistribute it, we're going to want to make this fit probably a sum of cubes pattern. Agreed? Can I take a 6 out? I guess does 6 go into 2,000? I don't think 6 is going to go into this, is it? I don't think so. I don't think it does. But the other thing you can think about when you're trying to undistribute something, you can cheat a little bit, legally cheat a little bit. We want to end up with the first term and the second term in the binomial incorporating perfect squares in it, right? Or perfect cubes, sorry. I added another column to the list here. So in addition to the perfect squares that we've been dealing with earlier, now we've got these perfect cubes also. So does it make sense then that I just want to undistribute a 2? Because then I'm going to get a 27x cubed. 27 is a perfect cubed. And then I'd end up with 1,000, which is 10 cubed. Okay, now notice that the perfect cubes, they grow pretty fast compared to the squares, don't they? Right, like 10 squared is only 100, but 10 cubed is 1,000. They grow, way, way faster. Okay, so if I undistribute a 2, then what I'm left behind with would be 27x cubed plus 1,000, right? Everybody see that? Good? Okay, so now we've got this GCF out front that we're done with. We've got this binomial. So the next step is you always want to ask yourself when you've got a binomial, which of the binomial patterns could that fit? We've only got 4, right? Sum of squares, which isn't even really a pattern, difference of squares, sum of cubes, and difference of cubes. Well, this is obviously a sum because it's a plus sign. So would it fit a sum of cubes or a sum of squares? Cubes, because I've got an x cubed in the first term, right? So our goal is to make this match the sum of cubes pattern. So let's write that one down just to remind ourselves. A cubed plus b cubed is equal to what? A plus b times minus ab plus b squared. Good. Okay, so we want to make that thing match. Everything inside the white factor, inside the brackets, we want to make that fit this pattern. So we've got our 2 out front that we're just going to leave there. And then inside the brackets, our goal is to get something cubed plus something cubed. Well, 1,000's easy. 1,000 is what cubed? 10. 27x cubed is what quantity cubed? 3x. I got to cube the 3 and cube the x, right? So now all we're going to do is just follow our pattern, right? Where we know what a cubed plus b cubed is. Here's the pattern. We're just going to make the substitutions that fit our situation, which is 3x and 10 for a and b. So we've got our, and don't forget the 2 out front. That's a very common mistake when we're factoring. We've got to carry that 2 out there. And then what are we going to get from this factor? Okay, what's our a going to be? Well, 3x, right? Our b is 10, so there's our binomial right there. Our binomial is going to be 3x plus 10. Okay, what about the trinomial? So a squared is what squared? What quantity am I squaring there for a? 3x. Okay, now here's another common mistake. What people a lot of times want to do for a squared is write it as 3x squared. What should it actually be? 9x squared, because I've got to square the whole thing, the 3 and the x. So I'm getting a 9x squared minus, okay, a times b. Well, a, remember, is 3x, and b is 10. So together, 3x times 10, I'm subtracting 30x, right? So all that stuff together, 30x, good. Okay, and then finally we've got b squared is just 10 squared, so what's that going to be? 100. And the whole thing, I've got it factored now, is still equal to 0, right? Okay, so now we're prepared to find our solutions because we can apply the zero product property, right? Well, the 2 doesn't give us any solutions, does it? That's just a constant. In fact, I could even divide both sides by 2 and get rid of that one if I want to. But here's a factor with an x in it. So what's my 0 going to be from this factor? If I set that equal to 0 and solve, what would I get? Let's see, if I set that one equal to 0, 3x plus 10 equals 0. If I isolate x, what am I going to get? Yeah, negative 10 over 3. Okay, subtract the 10, divide by 3. So one solution is negative 10/3. Okay? Good? Give me thumbs on that. Is that all good? Okay, now what about the other solutions? Because how many total should I get in this equation? How many total complex solutions should I have? Should have 3. Good, because I've got an x cubed there, right? So I need 2 more. How am I going to find the zeros of this factor, this quadratic one? Can I keep going and try to factor it and find magic numbers? No, you're right, Trey. How come? You're right. Because remember, it's an irreducible factor, right? The trinomials we get from our cube patterns are never going to factor. They're always going to give us i's when we find the zeros. So how do we do that then? Well, if they're not going to factor, how would we solve the quadratic equation we get when we set that equal to 0? Because that's how we ask the math gods for answers. If I want to know where this thing equals 0, I just write that as an equation and solve it. That's how they communicate with me, right? So if we do that, different color here. Let's do that. So we've got 9x squared minus 30x plus 100. We're going to set that equal to 0 and solve. Flip back to unit 4 and just go into quadratic mode. How would you solve that quadratic equation given that it doesn't factor? What's our ace in the hole we can always do for any quadratic equation? Quadratic formula, right. We'll just apply the quadratic formula, right? So we're going to get x equals negative b, so that's positive 30, plus or minus the square root of b squared, so that's 900 minus 4 times a times b, all divided by 2 times 9 is 18, right? Okay, so we got to simplify that. Let's split the fractions up, so I'm going to get 30 over 18, so we're just going to do that, right? 30 over 18 plus or minus. Now this is going to give me 900 minus 3600. So that's what? Negative 2700, okay. Plus or minus the square root of negative 2700 over 18. Okay, so the 2700, what do we get? We got to maybe we'll do couples go out, singles stay in for that. Okay, so when we split that up, we want to get perfect squares if we can. Well, what's one obvious perfect square factor of 2700? I could write it as a product of what two things? 27 and 100, how about? Yeah. So I could break it up into 100 times 27, which is good because that's giving me a couple of tens. How about the 27? 9 and 3, good. And the 9's going to break up into a couple of 3s. So what do we end up with then? We get a couple of 10s, couple of 3s, and a single 3, right? So the square root of 2700, I'm going to get a 3 as an outside number and a 10 as an outside number, right? So we'll keep going here. on the top, square root of 2700 is giving us 30 outside, right? 3 and a 10. And inside, we get a 3. And then what do I do with that negative sign inside the square root? Comes an I. And then I've got on the bottom an 18. 30 over 18 reduces to what? 10 over 6, which reduces to 5 over 3. Okay. So we get the solutions then x equals 5/3 plus or minus 5 root 3 over 3. Because look, I get the same. There's a 30 over 18 that I can reduce. Those are outside numbers, so I can reduce that fraction, right? So 5 radical 3 over 3i. How many solutions are contained there? 2. One for the plus, one for the minus. It's a complex conjugate pair, isn't it? 5/3 plus 5 radical 3 over 3i. There's a complex number. And 5/3 minus 5 radical 3 over 3i. Okay? Total of 3. We got one real solution, negative 10/3, and 2 imaginary solutions in a complex conjugate pair. Give me 1 to 5 on that. Okay? Okay? Not bad. Not bad. Okay, what would we do with one like this? This is kind of a tricky one. Because really, now think about this. Our goal here, if I want to solve this thing, first I'm going to put it into standard form. Agreed? So I'll set it equal to 0. That's what I'm sure that's what you all would tell me to do. So we're going to get x to the 6th minus 64 equals 0. Now I got a binomial on the left side, so I've got to try to factor that using my patterns. Okay, so which pattern could I use there? X to the 6th minus 64. I've got a minus, so it's going to be a difference pattern. Could I write that as a difference of squares or a difference of cubes? Or what do you think? Could I write x to the 6th minus 64 as something squared minus something squared? 64 would be what squared? 8. Okay. What about x to the 6th? X to the 6th would be what squared? X cubed. So I could write it as a difference of squares. Right? I could write it as something squared minus something squared, and I could use that pattern. Could I write it as a difference of cubes? I could, right? Because 64 is 4 cubed. X to the 6th is what cubed? X squared cubed. So I could do this either way, right? So far it seems like I've got a couple good choices, right? So let's try this one first. What if we do the difference of squares? After all, that's the easier of the two patterns, isn't it? The difference of squares pattern. So a squared minus b squared factors into, my a in this case is just x cubed, and my b is 8, right? So what's that going to factor into? X cubed minus 8 times x cubed plus 8, right? Okay, agreed? That works out okay. And we could go from there now. We could split each of these up. I could rewrite that 8 if I want to as a 2 cubed in each case. And look, I've got a difference of squares pattern, x cubed minus 2 cubed, and times a sum of squares pattern, x cubed plus 2 cubed, right? So I could split each of those again, okay? What am I going to get if I do that? What am I going to get from this first one? I'm going to get a binomial times a trinomial. So again, it's x cubed minus 2 cubed. How's that one going to factor? What's my binomial going to be? Yeah. Everybody agree? X minus 2. Because x is like my a and 2 is like my b, right? Times what? Ella, what am I going to get for my second one?
X squared.
Good, good. It's got to be plus, right? Plus 2x, good. Plus 4, good, 2 squared. Everybody agree? Good job. Okay, so there we split that first one up, and now we're done, right? I've got a linear factor, I've got an irreducible quadratic factor. Let's do this one. Let's make this one green though, just so we can keep track. How's that one going to factor? X cubed plus 2 cubed. What's that one going to be? Grace? Go ahead. Go ahead, Grace. Plus 2 times plus 4. Good. Okay, and that whole thing is equal to 0, right? And now all we'd have to do is just set each of those factors equal to 0 and solve. Okay? How many real zeros am I going to get out of this? I get 6 total. I get 6 complex zeros. How many of those are going to be real? How come, Carson? Well, because we can see that's going to be real and that's going to be real. Are those, any chance those are going to be real? No, right? That always gives me complex conjugates. That one's always going to give me complex conjugates. So I'm only getting 2, aren't I? So the 2 real ones would be x equals 2 or x equals negative 2, right? If I want to find these, I've got to go set that factor equal to 0 and solve using the quadratic formula again, right? So let's do that one. So if I set that equal to 0 and I solve, I got to use quadratic formula, right? I can't factor it. So I'm going to get x equals negative b plus or minus the square root b squared minus 4 times 1 times 4 is 16, right? All over 2. So I'm getting x equals, if I split this thing, negative 2 over 2 plus or minus the square root of negative 12 over 2. Okay, which is going to give me what? Negative 1 plus or minus. What's the square root of 12? Yeah, 2 radical 3. Everybody agree? Square root of 12 is the square root of 4, which is 2, times the square root of 3, right? So I'm getting 2 times the square root of 3 over 2. And the negative inside becomes an I outside. I can cancel the 2's, and look what I get. X equals negative 1 plus or minus square root of 3i. Well, there's a complex conjugate pair, 2 imaginary solutions. And then I could do the same thing. We won't take the time to do it, but I could do the same thing there, couldn't I? And I'm going to get a complex conjugate pair also. Okay, agreed? And that would be 6, okay? Give me my 6. Okay, what about this one? Well, we could have gone this route also, right? Let's go back. What if we had split this up as a difference of cubes? Okay, well, we can do that. I've got a cubed minus b cubed, where a is x squared and b is 4. How's that going to factor? How's that one going to factor? Annika, you got that one. I gave you a tough one. So my a is x squared and my b is 4, and we're using a cubed minus b cubed. Okay, anybody want to, this is a tough one. Anybody want to try this? Think you got it? You're going to say it. Say it again. 4, there you go. There's my, good job. There's my a minus b times x to the fourth, I'm going to get an x squared squared, which is x to the fourth, plus 4x squared, right? Plus 16. Good. B squared. Okay, now what about this one? Okay, so we might be tempted. Here, I'm going to go to another page with this one. Seems like it's going to be fine, right? I mean, we just got to somehow get the same 6 solutions out of this. But there's a really important moral to this story. One of these is going to work way better than the other one, and that's what you're going to see. I bet you can guess which one's which. Okay, so what about this guy? Let's keep going. So we could apply the zero product property. Now, here's another kind of important thing to consider. So x squared minus 4, I could break that down as a difference of squares, couldn't I? That's x squared minus 2 squared. I could factor that into x minus 2 times x plus 2, and I'm just going to get the zeros 2 and negative 2, right? Okay, I don't have to, though. If I'm not being asked to factor this thing completely, I don't necessarily have to. I'm just trying to find the solutions. So I could just say, okay, I've got a quadratic factor here. Let's just ask the math gods for the zeros by setting it equal to 0 and solving. Well, I don't have to factor that. I could just directly isolate x too, couldn't I? Because for quadratics, that's a valid solution technique that we learned in Unit 4. If I have a quadratic equation where I can point to a single x, I can always find all the solutions, all complex solutions, by isolating the x. It works for quadratics, okay? So what would my steps be to isolate the x there? Add 4, and then, yeah, square root both sides. Okay, so that's going to give me x equals, when I square root both sides, I have to include a plus or minus. Square root of 4 is 2. So there's my 2 real solutions, just like I got last time, right? I got negative 2 and positive 2. Same real solutions. Okay, here's where things start to get a little rougher, though. How about this one up here? How am I going to solve that? I've got x to the 4th plus 4x squared plus 16 equals 0. How in the world am I going to do that, right? That doesn't sound very fun. There is a way. I could use the quadratic equation, only this time this is quadratic in x squared instead of x, right? Everybody see that? So instead of getting x squared plus 4x plus 16, I've got x squared squared plus 4x squared plus 16. So if I were to use the quadratic formula here, what I'm really solving for are x squareds instead of x's, because those are the things that are showing up being multiplied by a and by b and c, right? Everybody get that? We'll talk more about that tomorrow, about using this kind of a technique. But I just want to show you this. Even if we do, it's not going to work well. Aubrey, you have a question?
Yeah, so you can't, is it not possible to just take out all the extra squares?
You can't take them out, but like I could think of it, so think about, instead of calling that x squared, let's just call it hand. I've got hand squared plus 4 hand plus 16, right? I could solve using the quadratic formula. This time the song would be, instead of saying x equal, say hand equals negative b, right? Whatever is behind my hand is going to be what we're setting equal to the quadratic formula. So we'd get x squared equals negative b, so that's negative 4 plus or minus square root b squared minus 4ac. That's a 16 actually, isn't it? We're going to replace that with a 16. 4 squared is 16. So that's going to give us 64 all divided by 2. Okay, now look, we're going to have big problems here because I've got x squared equals negative 2 plus or minus. I've got the square root of negative 48, right? over 2. I'm going to have x squared equaling expressions with i's in them. How am I going to do that? I'm going to have to end up square rooting numbers with i's in them. That is way above and beyond the level of an Algebra 2 class, right? So could we all agree we're going to stop, right? This is a bad idea. So the moral of the story here is when we've got something where we have an option of either using the sum or the difference of squares or the difference of cubes, like we've got a big power of x, like x to the 6th or x to the 12th or something like that, which one are we always going to use first? Difference of squares every time, right? We're always going to use the easy one as many times as we can and only have to use the harder pattern at the very end, like we did in the first example. Everybody get that? Okay. So this is just say no to using difference of cubes too early. It causes big problems. Okay. All right. I don't want to do that. Okay, I think, I skipped one. There's one I wanted to do. What about that one? So we'll do one more example. How about that one? X to the 4th minus 16 equals 0. What would I do there? Say it again. Start with difference of squares. If we can use difference of squares first, we're always going to, right? So we could make this difference of squares. X to the 4th is what squared? X squared. X squared squared, right? Minus what squared? 4 squared. Okay, so then difference of squares pattern is what? That's my A and that's my B. Plus 4, so I get A plus B times A squared minus, A minus B, right? X squared minus 4. And I want to know when does that whole thing equal 0. Okay, well, now I've got it down to where I've got quadratic factors. As soon as I get to quadratic factors, I can set them equal to 0 and solve. I can either choose to factor further or not. And in this case, I can't even factor further, right? So if I set this equal to 0 and solve, x squared plus 4 equals 0 when x squared equals negative 4. So what does x equal then? Plus or minus if I square root. Say it again. 2i, because I'm taking a square root of a negative. Everybody see that? Right? When I square root both sides, look at that. I've got a square root of a negative. So I'm getting plus or minus 2i. Okay, so there's one set of complex conjugates. How about this one over here? This is a little better. X squared minus 4. If I solve for x, what am I going to get there? X equals plus or minus 2, right? I'll add the 4 to the other side and square root it. So I'm just doing x squared equals 4, so x equals plus or minus 2. I get 2 real solutions and 2 imaginary solutions. Okay, good. Hang on. Call you back in a second in class. Okay, bye. Okay. All right, so make sense? Question?
How come we couldn't just add 16?
Okay, so the question is, how come I couldn't just add 16 to the other side? It seems like a good idea. So I get x to the 4th equals 16. Well, okay. Because the answer is, if it's bigger than quadratic, I can't necessarily guarantee I'm going to get all the solutions by isolating the variable, right? In this case, you actually can, right? Because if I square root both sides, I would get x squared equals plus or minus 4, and I could take both of those equations and solve it. But it didn't work. We did an example last week where we had x cubed equals 8, right? Or we had x cubed minus 8 equals 0. Actually, here, I'll make it up. So say we had this one. Say we had x cubed plus 8 equals 0. If I try to isolate the x, I get x cubed equals negative 8. If I cube root both sides, I don't do a plus or minus when I cube root, so I only get one solution, x equals negative 2, but I know there should be 3. See what I'm saying? So if I have a polynomial that's bigger than quadratic, I cannot guarantee that by isolating x, I'm going to get all of the solutions. I may only get the real ones. Okay? Make sense? Okay? And it worked in this case, but it wouldn't have worked if I had had something like x to the 6th equals 64. If I tried to just take the 6th root of both sides, that one's not going to work. I'm only going to get the real solutions. I'm not going to get all the imaginary solutions. I'm only going to end up getting 2 solutions out of this whole thing instead of 6. Okay? That answer your question, Kylie? Yeah. So if it's bigger than x squared and it's a binomial, you have to factor it. You can't just isolate. But once you get to the point in a problem where I've got factors that are quadratic, then I can always, if they're quadratic factors, I can choose to just isolate x if I want to, and it'll always work. Okay, but until you get them down to where they're x squareds, got to keep factoring. Okay? Good question. All right, I'm done. I don't know how much time there is, but whatever time there is left, you can work. Probably not